We're looking at the alternating series test in this section, and the alternating series test is designed specifically, as you might guess, is to test alternating series. Now, specifically, alternating series have signs that change from positive to negative to positive to negative. So an example of something like this would be something like maybe 1 minus 1/2 plus a third minus a fourth plus a fifth. You kind of get the idea here. And this pattern would continuing along indefinitely. Now some of these series, this one is specifically alternating, it's starting positive and then goes negative. Some could start negative and then go positive, and it's still considered an alternating series. We have others that might go positive, positive, negative, negative, positive, positive, negative, negative. We don't call those alternating series because the signs are not changing every single term. So you kind of have to look specifically at what we have and make sure that the signs do alternate as predicted. This particular series that we have here looks like we could rewrite this in terms of summation notation. Looks like we could start with k equal 1 to infinity. My numerator always looks to be a 1, and then my denominator just looks like whatever the k value is. So this looks like 1 over k. So this would produce 1 over 1, 1 over 2, 1 over 3, all addition. Now the alternating part we usually take care of with a -1 to some power. Now the power could either be k or k plus 1 depending on where we're starting with our indice. We're starting here with a 1, so we want our first term to be positive. So if we want our first term to be positive, and if we put a k here, we'd have -1 to the 1, which would produce a -1, so my first term would be negative, so that's not what I want. Now if I add 1, that should work great. So if I plug in a 1, so if I plug a 1 into the exponent, 1 plus 1 is 2, -1 quantity squared produces our positive 1. Now for my next term 2, 2 plus 1 is 3, a negative to an odd power produces a negative value, so we're on our way now. So again, this exponent is usually k or k plus 1. It just depends based on whether we're starting with a positive or negative value. Now we talked about the alternating series test, but we didn't talk about its specifics, so I'm going to call this AST, alternating series test. So the alternating series that we want to test on this, it could be something that starts -1, let's say, to the k, or -1 to the k plus 1. That part doesn't matter. That part just means, this piece just means it's alternating. So this series converges under two conditions. The first condition is the terms of the sequence are non-increasing. Now I usually think about this as decreasing. Non-increasing means the terms could be equal as long as they're not getting larger, or they need to get smaller. So non-increasing, and again I usually think about this as decreasing, but non-increasing is the correct way to say that. And they're non-increasing in magnitude, which means we don't consider their positive or negative value, just their magnitude. And the shortcut way of saying this is the next term is less than or equal to the current term. That's the first criteria. The second criteria, if I take the limit as k approaches infinity of the absolute value of the series, notice I just have a sub k here, I don't have the alternating part, I have to get a 0 here. Now if this doesn't happen, then I can't say anything about this test. The alternating series test fails. So this is the alternating series test. Now there's a couple notes we want to make here. This is only a test for convergence. It's not a test for divergence. So we can't say, oh, this failed, therefore it diverges. Usually we have to try some other different test. So that's the note we want to make here. If the alternating series test fails because of basically number 2 here, because the limit as k approaches infinity of a sub k does not equal 0, and this should look kind of familiar for you right now, then the divergence test succeeds. Because remember, the divergence test said take the limit, and if we get the limit of the terms not going towards 0, then what we can say is the series diverges, and so that's what we're going to say here. Then the divergence test kicks in, and the alternating series diverges. So be on the lookout for that. And this, of course, works for that second reason. Now, if I have something not working or failing right here because of the first reason, what ends up happening then is I need to find another way to test this particular series. And maybe I could test it with the nth term test for divergence, or the divergence test, or some other test from our list. But that's the alternating series test. Let's go ahead and look at a few more examples. I'm not sure why that showed up. And with our few more examples, we'll start to see some that fail and some that succeed for different reasons. Let's go ahead and look at the one that we checked up above, the very first one that we tried. We looked at the series -1 to the k all over 1 over k times 1 over k. So that was this test right up here. Now we're changing our indice from k to k plus 1, and all we have to do to substitute for that is to say, I guess we could make this a k plus 1 to make it consistent with the one on top, but it wouldn't matter. It would just mean that we're starting with a negative instead of a positive value. So clearly this is an alternating series. So because it's an alternating series, I will use the alternating series test. That seems to make sense. So first criteria, it has to be non-increasing. And there's several different ways that I can show this. I can't just say, yep, non-increasing. I have to establish that or show it. So the way that we do that is we're trying to show that the next term is less than or equal to the current term. Well, one way that we could show that is we could compare term by term, but of course there's a lot of terms to compare. There's an infinite number of terms. So one way I like to do these is to take a derivative. Now I understand these are not continuous functions, if these are integer value functions, but I'm going to go ahead and take the derivative as a real value. I'm going to assume that whatever I come up with an integer will also be true for the continuous function. So let's go ahead and take the derivative of 1 over k, which is k to the -1. That derivative is -1 over k squared. This is always going to be less than 0. So the derivative is less than 0, which means the function is always decreasing. So the derivative is less than 0, which means it means the slopes of the tangent lines are always negative, which means the function is decreasing, which means the function is decreasing. Okay, so the first thing is true, so we put a big check mark there, but you can't just say it, you have to establish it, you have to show it. The second piece here is the limit as k approaches infinity of 1 over k, when we're just looking at the non-alternating part, so we're ignoring this negative. This does equal 0, and that's the second criteria. So we could say, therefore, the series converges by the alternating series test. So the things that are important here, we name the test, we show the criteria for the test. So we name the test, we show the criteria for the test, we show how our series either meets or does not meet the criteria, and then we draw a conclusion. And this is what you should have for every test that you do. Name the test, show the criteria for the test, show how it meets the criteria for the test, and then kind of continue from there. This is kind of interesting. I don't know if you caught this or not. We have here that this series converged, but if you remember, if I just look at 1 over k, this is a divergent harmonic p series. So what we have here then is that the series, the alternating harmonic p series, if we want to call it that, diverges, whereas the non-alternating converges. So that's kind of interesting. I'm sorry, the alternating converges, the non-alternating diverges. And we're going to get into the point of fact where we talk about absolute and conditional convergence toward the end of the lecture. Let's go ahead and look at another example. And again, we're looking for converge or diverge. So the series here would be, let's go -1 to the k plus 1 times 1 over k squared. So this is the alternating part, this is the alternating component, this is the non-alternating component, that's the a sub k. And we'll go k equal 1 to infinity here. So this looks like it is definitely alternating. So let's go ahead and look at this, the alternating series test. The first thing that I have to show that this is non-increasing, and there's several different ways I can show non-increasing. I could compare term by term, or I could take a derivative. That would be another option. But basically non-increasing means the next term is less than or equal to my current term. So I think I'd like to do this with a derivative again. 1 over k squared is k to the negative 2. When I take the derivative, I bring the exponent down and then I decrease it by 1. So this is negative 2 over k cubed. Now all of the values of k that we're looking at, if you come up here, are positive. So k would equal from 1 to infinity. So it makes sense then that that denominator would always be positive and the numerator is always negative. So this is a negative over a positive. This k cubed will never be negative because k is never negative. I'm only looking at positive values of k. So this is always going to be less than 0. Therefore, we can say the same thing that we did up here. The derivative is less than 0. Therefore, the function is decreasing. And that's what we wanted to show. Decreasing, non-increasing. Non-increasing means I could have equality as well from term to term. So that first criteria has been established. Second, I need to take the limit as k approaches infinity of 1 over k squared, which definitely equals 0. So that criteria has been met. And I guess, one thing I didn't do here is I didn't establish why this equals 0, and I should do that. And it's because the degree in the numerator is less than the degree in the denominator. And I should show that up here as well, except it's under here. So make sure you're establishing these on your handwritten homework and your exams the same way. So I should be able to draw a conclusion here that I should say, therefore, the series, and this was negative 1 to the k plus 1 times 1 over k squared, converges by the alternating series test. Okay, so again, going through and establishing, you want to name the test, state the criteria for the test, show how your series either meets or does not meet the criteria, and then draw a conclusion. Okay, let's look at another one. This next one is a fun one because instead of being given the series, we get to create the series on our own, given the values from the series. So for instance, we could be given something like 2 minus 3 halves, and it's alternating, so this switches to plus 4 thirds minus 5 fourths plus 6 fifths minus 7 sixths, and I think you kind of get the idea of this trend. So if we were to write this out, then we can certainly see that it's a series. I'm not going to worry about what we're starting with from k quite yet. I know it's alternating, so I need some sort of an alternating component. And then it looks like to me the numerator 2, 3, 4, 5 is increasing. The denominator is increasing as well, but it's starting at 1, so this is an implied 1 here. So if we were to write this out, it looks like to me we could start at k equal 1, and my denominator would start with k then, and my numerator would be 1 more than that, k plus 1, because if you notice my numerator is always 1 more than the denominator. Okay, so this is the series that I want to test. It's definitely alternating. It's starting positive, so let's go ahead and put a k plus 1 up here, because then my series will alternate correctly. So when I look at this, it's alternating, so I'm going to go ahead and try the alternating series test. The first criteria, I have to show that this is non-increasing. And that's basically saying the next term is less than or equal to the current term. In order to establish that, I could take a derivative of the non-alternating part, or I could compare term by term. Now there's a lot of different ways that you could do these. I like to look at the derivative first if we can, because the derivative is usually the easier part. This is a quick quotient rule. So I'm taking the derivative with respect to k, not x here, of k plus 1 over k. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So if we simplify this, I have k minus k, they cancel, minus 1, so I end up with negative 1 over k squared. Well, this is definitely less than 0 because I have a negative over a positive. So this is a negative over a positive, so this is definitely less than 0. Therefore, the derivative is negative. So the series is decreasing. Okay, now it's never equal to 0, so it's definitely decreasing, so I can say that that's non-increasing as well. So that criteria has been met. Second criteria, the limit as k approaches infinity of k plus 1 over k, that's equal to 1. Why? Because the degree in the numerator equals the degree in the denominator. And this, the alternating series test fails. Because I had to have that equal to 0 in order for the alternating series test to be successful. So this just failed. Well, we have to do something. We have to figure out what this does. Does it converge or diverge? The alternating series test fails, but remember, if we scroll back up and have a look here, there's a note. And this note says, if the alternating series test fails because the second component, the limit, does not equal 0, then the divergence test kicks in and the alternating series diverges. So that's what we want to call on. So the alternating series test fails. However, the divergence test kicks in, and we've already shown the divergence test equals 1, which does not equal 0, therefore it diverges by the divergence test. So our conclusion then is the series, and this, again, this one was interesting because we got to create our own series. Negative 1 to the k plus 1. I think this was k plus 1 over k. Diverges by the divergence test. Okay, so that's an example of it diverging for the second reason. We haven't looked at one yet that the alternating series test fails because of the first reason. And if that happens, we have to have something else to do. We have to have another test that we can work with on it. Our next one, we're going to be using a log function. So let's look at the alternating series test, and I want you to note this one is starting at 2. So typically we start these at 0 or 1. This one's starting at 2. So negative 1 to the k, negative 1 squared, we start with a positive value. And then I have the ln of k over k. Now one reason this happens, remember, if we plugged a k equal 1 in here, the natural log of 1 is 0 and our first term would be 0. So again, we're starting at 2. So this term, negative 1 to the k, makes this an alternating series. So let's go ahead and start testing this with the alternating series test. First thing I need to show is that this is non-increasing. Non-increasing means basically that the next term is less than or equal to my current term. And I can't just say it's true. I actually need to be able to establish that. So a derivative is a good way to do that sometimes. We'll see if it helps us out here. So this is going to be a quotient rule, so I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So my derivative then is k over k cancels, so I'm left with 1 minus ln of k all over k squared. Now remember, we want to show that this is negative. Well, if we start with 2, the natural log of 2, well actually let's start with the natural log of 1. The natural log of 1 is 0. Okay, the natural log of 2, I'm not sure, that's some decimal line. I could look it up, but we want to be able to work with these kind of thinking on our feet here, not always having a calculator to check with. The next one I know is the natural log of e. The natural log of e is 1, so 1 minus 1 would be 0. So anything greater than e, this is going to be a negative numerator. So E is 2.72 about, approximately. So it looks like to me that this would be decreasing for k greater than or equal to 3. So what I can do here is say, you know what, it's increasing that first term is positive, but it decreases for all k greater than this fixed integer of k equal 3. So now we can say it's decreasing in this certain case. So again, thinking on our feet here, we know the natural log of 1 is 0. I'm not sure what the natural log of 2 is. I could look it up, but I do know that the natural log of E is 1, and 1 minus 1 is 0. All other natural logs above that are going to be positive. So just looking at this again, this is your natural log graph, just a quick sketch of it. This is 1, so the natural log of 1 is 0. 2, we're not sure what's going on. 3 is somewhere over here, and E is right in here. And so after this point, we're saying at E that this is starting to be positive. This is a large positive number, and when we subtract 1 minus a large positive, the overall fraction goes negative. Now what we're looking at here is just the natural log graph, not 1 minus the natural log graph. So make sure that we're clear on that. So this is the natural log of x. So therefore, what we can say is the function, or the alternating series component, is decreasing or non-increasing. And it's true for k greater than or equal to 3. Now the second thing we need to establish then is the limit as k approaches infinity of the non-alternating portion is equal to 0. But when we go ahead and take this limit, I get infinity over infinity, and I'm going to have to use L'Hopital's. So this is indeterminate L'Hopital's, and I have to say that I'm using L'Hopital's, and I need to be able to say why I'm using L'Hopital's, or why I can use L'Hopital's. So this leaves me with the limit as k approaches infinity. The natural log of k, the derivative is 1 over k times the derivative of k, and down here the derivative of k is 1. So this is the limit as k approaches infinity of 1 over k. And as k goes toward infinity, this goes toward 0 because the degree in the numerator is less than the degree in the denominator. So this is true as well. So both criteria have been met. Therefore, the series, and again this started at k equal 2 to infinity, negative 1 to the k, natural log of k over k, converges by the alternating series test. So again, name the test, show the criteria for the test, show how the series that you're looking at either meets or does not meet the criteria, and draw a conclusion. If the conclusion is, I don't know, you have to try another test. If the conclusion is converge, you're done, diverge, you're done. Now, when we're talking about a series and a sum of a series, sometimes what we can do is try and estimate what the sum of the series is based on a few terms, and sometimes it might be 100 terms or maybe just 10 terms. But basically we can talk about a remainder that we have then if we estimate the series using the first n terms. So let's talk about remainders in alternating series. So remainders in alternating series, there's a couple important things that we can look at, and I'll go ahead and write out these definitions, but looking at an example is probably going to be the most helpful here. We have a theorem, and I don't like to give these theorems a name because they change from book to book. It might be theorem 9.2 in one book and 9.20 in another book. So there's a theorem that says let us have some sort of a series that's alternating, k equal 1 to infinity, and this is the alternating portion of the series, and this is the non-alternating portion. Okay, and let this be a convergent alternating series. Now the important thing here is we realize it's already been established to be convergent. Okay, so we have a convergent alternating series with terms that are non-increasing, again, if you want to think about that as decreasing, you can as well. Just remember that if you do that, decreasing doesn't assume that they can ever be equal to each other. So non-increasing in magnitude. So that means we're not really considering whether they're positive or negative, just what the value is, that it's always decreasing or getting smaller or equal to. So what we're going to do is we're going to let the remainder of the nth term, so r sub n means the remainder of the nth term, is equal to the series total, meaning what is the series converging to, minus the partial sum of the nth term. So this would be the remainder. That we would use when approximating the value of that series by the sum of its first m terms. Well, if we have all of this going on, then what we can say let's see here, my stylus went away, let me see. Then that magnitude of the remainder, that's the absolute value, would be the magnitude, it doesn't matter about the sign, will be less than or equal to the a sub 1 term. So let's go ahead and write that out in words. The magnitude of the remainder is less than or equal to, so that notation of course you're familiar with, the magnitude of the first neglected term. Now when we talk about the first neglected term, what we're getting after there is the first term that's not included in that sum. So it means the next term. Now we don't have absolute value signs here to talk about the magnitude, because if you notice we're not talking about the -1 to the kth part, we're just talking about the term, not the sign of the term. Now these are difficult to look at in terms of all of these definitions. They're not so bad, however, when we actually work out a problem. So let's go ahead and look at a problem to try and clarify some of this. So we earlier did a series k equal 1 to infinity, -1 to the k, I think it was k plus 1 all over k, and then we had a 1 right here as well. This was equal to 1 minus 1/2 plus 1/3 minus 1/4. I think we did this right at the beginning of the lecture. Okay, so this same thing. Well, as it turns out, this series is equal to the natural log of 2. So if I look at the sum of this infinite series, it's the same as the value for the natural log of 2. Well, what I want to do here is to talk about how many terms of this series is needed. You know, just the first term, do I need just the second or the first 3 terms? How many terms of this series do I need in order to approximate the natural log of 2 with a particular amount of error? So that's what the question will be. How many terms from this series are required to approximate the ln of 2, and again this series is equal to the ln of 2 in its infinite form, with a very small amount of error. So with an error of 10 to the -6, let's say. So 10 to the -6. Well, the first thing that we need to do in order to apply what we just learned up here is we need to know that this is a convergent alternating series first. So the first thing that I'll do is I'll establish that this is convergent by the alternating series test. So let's go ahead and look at the alternating series test. The first thing that I have to show is that this is non-increasing, which means that the next term is less than or equal to the current term. And so the way that I would do this is by taking a derivative And I'm really only, and we've looked at this before actually, if you scroll back through some of the problems, I'm really looking at the non-alternating portion, so that's the 1 over k, which is k to the negative 1. So the derivative is negative 1 over k squared, which is definitely less than 0. And we're looking from k equal 1 to infinity, so definitely less than 0. So this implies that the derivative is less than 0, therefore the function is decreasing. Now, if you were to graph 1 over k, remember 1 over k or 1 over x would look something like this. And so we could also look at a graph as well, but a quick derivative is an easier way to go because we don't always know the graph. So this first criteria has been met. The second criteria, the limit as k approaches infinity of 1 over k equals 0, check. I needed that to be true as well. So therefore the series negative 1 to the k plus 1 times 1 over k converges by the alternating series test. Okay, so if we go back up here and check, we have this first criteria met. Has to be convergent alternating series with terms that are non-increasing. So we've already established that as well. Then we can start talking about the remainder part. Now I think in order to talk about this remainder part, it's easier to me to kind of look at a few terms here. So I have 1 minus 1/2 plus a third minus a fourth plus a fifth minus a sixth plus a seventh. You kind of get the idea here. So what ends up happening is this keeps going, and I'm going to go out to the nth term. So this would be the nth term. And then right after that nth term is the n plus 1 term. So this would be n plus 1 all over n plus 1. So this is the nth term, this is the next term after the nth term. So what I want to look at here is to talk about what's happening. This, all of these first n terms, if I add those together and combine those, this would be the sum of the first n terms. That's called S sub n, the nth partial sum. Okay, now this last one that we have here, there's a couple different names for that. It's the n plus first term, and it's also known as R sub n. Okay, it's the remainder that we would see after the nth term. So what we have then from our formula, from our theorem up above that we were looking at, is the magnitude, or the absolute value of R sub n, is equal to the partial sum minus S sub n. And we know that that has to be less than or equal to the a sub n plus 1 term. So the absolute value of R sub n has to be less than or equal to the a sub n plus 1 term. So what we know then is R sub n, that's this value right here, that's 1 over n plus 1. Again, this is your implied 1 right here. So this is 1 over n plus 1, has to be less than or equal to the a sub n plus 1 term. So we already have established what we want that criteria to be up in the original problem. This was that 10 to the negative 6. So we want it to be less than 10 to the negative 6. So how many terms am I going to have to go out in order for this to happen? So we need to figure out how many terms to go out. So let's have a look and see what we can do to work with this. A couple different things that I can see that we could do here. First of all, 10 to the negative 6, if I rewrite that without a negative exponent, it's 1 over 10 to the 6th. And then from there, we can think about this as cross multiplying, and we get something like 10 to the 6th would be less than or equal to n plus 1. We usually like our variables on the left, so that would be n plus 1 has to be at least greater than or equal to the 10 to the 6th term. So what we have then is 10 to the 6th, that's a 1 with 1, 2, 3, 6 zeros. That's a million terms. So a million terms are needed. to approximate the natural log of 2. With that error that we mentioned, with an error less than 10 to the negative 6. Okay, so that's kind of the interesting part, some of the interesting things we can do about error and remainders using that theorem. It's a lot easier when you put some numbers to them. Another thing that makes it easier is if you actually write out the terms and kind of show yourself, you know, this is S sub n, this is R sub n, and we're trying to figure out how many terms that we'd have to go out to make this happen. So again, writing out the terms can be helpful there. Now there's one other thing that we need to look at in this particular section, and that's the idea of absolute and conditional convergence. So if we talk about absolute and conditional convergence, actually, let's do one more of these with the remainder, because you might run into some problems, and I want to make sure you have quite a few to go off of. And the reason I like this one is we get to rewrite our own series notation. So 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, and you kind of get the idea of what's going on here. And so if we look at k equal, we could go 1 to infinity. This is really 1 over 1, so this is an implied 1 here. So I get that there's this alternating part that we'll figure out, and then in the denominator it looks like to me I have k factorial, and the numerator is a 1. Now I want this to start negative, so I think I could go negative 1 to the k, and if I'm starting my indice at 1, I have negative 1 to the 1, which starts negative, so this works pretty slick. So for this one, let's go ahead and find an upper bound. For the magnitude of the error. Now if you remember, that magnitude of the error was absolute value of R sub n. In approximating the value of the series with n equals 9 terms. Okay, so this time we're given the number of terms. So if we wanted to write these out, I'll go ahead and write them out again. So this is negative 1 plus 1 over 2 factorial, 1 over 3, 1 over 4, 1 over 5, 1 over 7, 1 over 9. And I'm going out a little bit further here because we're doing the first n terms for 9 terms, so I wanted to go out to at least 9. Now when we look at this, this is S sub 9 then. This is the 9th partial sum. That means if I add together the first 9 terms, I'd get S sub 9. So if we look back up here, get this to scroll up, this was the sum of the first n terms. So down here, S sub 9 is the sum of the first 9 terms. Okay? And then what we have here, everything from here after, this ends up being kind of our remainder. So this is R sub 9. This is what remains after the first 9 terms. So R sub 9, if we want to talk about the magnitude, would be equal to the absolute value of S minus S sub 9. So kind of keeping those things in mind, the absolute value of R sub 9, the remainder there, the magnitude, absolute value of S minus F sub 9 has to be less than or equal to A sub 10. So rewriting this, R sub 9 is this value right here. So R sub 9, it was 1 over 10 factorial. And then what we have is we want this to be less than or equal to that A sub 10. So 1 over 10 factorial, you can actually grab a calculator to calculate that. That would be 1 over, or 1 divided by 10, 10 times 9 times 8 times 7, etc. This is about 2.8 times 10 to the negative 7. It's a very, very small number. So that's the upper bound for the magnitude of the area. That's the highest it could be. It could be somewhat lower, but that's the upper bound for it. And again, we find that by our R sub 9 right here. So that's another example of where we can use these remainders. Okay, now let's go ahead and talk about absolute and conditional convergence. When we're talking about absolute and conditional convergence, we're checking for absolute values, as you might notice in the name absolute. So what we have here then is if the absolute value of a series converges, then the series itself, a sub k without the absolute value, converges absolutely. It's not true that just because a series converges means the absolute value will converge as well. Also, if the series absolute value diverges, and I have to have one more criteria here, and the series itself converges, then the series itself, not the absolute value, converges conditionally. Okay, so if a series converges, I check its absolute value, and if the absolute value converges, then the original series converges absolutely. If the absolute value diverges, then it converges conditionally. Now, what about divergence then? Well, if the original series diverged, then I don't even need to check the absolute value. So those are some of the things that we have here. Now, there's a couple of other things that fall into play with the theorem, and again, I don't like to name these theorems because they change names depending on which textbook you're looking at. But if we have that the absolute value converges, so if we check the absolute value first and it converges, then that automatically means that the series converges. And then we have something else that we can say here then, is if the series itself diverges, then we can automatically say that the absolute value will diverge as well. Now the ordering of these is important. Here we have the absolute value converging, then the series itself converges, but this is not absolute value here. This says if the series diverges, I don't even need to check the absolute value. I already know that it diverges. Now there's a couple of other things that we can say here. Absolute value, absolute or conditional convergence is only relevant for alternating or mixed sign series. Now the mixed sign series that I'm referring to here are the positive, positive, negative, negative, ones that don't alternate every single term. So absolute and conditional convergence is only relevant for alternating or mixed sign series. Okay? If we have a series of all positive terms, and most of the series that we look at do have all positive terms, but not all. So if a series of positive terms converges, what we have then is that it converges absolutely by default. I don't need to check the absolute value because all the terms are already positive. So that's one of the things that we can kind of count on here. Let's go ahead and write that out. Okay, so that means we don't even need to check for absolute convergence. We know it happens. And then conditional convergence doesn't even apply. Meaning I don't need to check for it. I don't even need to refer to it. It doesn't even make sense because if it's all positive terms, if I take its absolute value, I get the same series back. Another thing all those convergence tests that we've learned earlier. So the convergence tests that we've learned earlier, and we've learned a lot of them. Let's say we've had the ratio, the root test, we've had a p-series test, we'd have a divergence test, we've had the integral test, we've had the comparison, we've had the limit comparison. All of these tests are what I can use then to check the series that I'm talking about up here of all the positive term series. And all of those can be used when I'm checking for the absolute value of an alternating series when I'm talking about whether we have absolute or conditional convergence. So basically these are used to check for absolute convergence as well. So something to keep in mind. These tests keep showing up over and over again. Well, again, what we want to do to try and clarify some of these definitions that I think are a little bit difficult to work with are to look at some particular problems. So the first one we want to look at, let's go ahead and look at whether this diverges, converges conditionally, or converges absolutely. So the series that I want to look at is k equal 1 to infinity. And let's look at negative 1 to the k plus 1 times 1 over the square root of k. So if I want to know if this converges absolutely or conditionally, I'm not talking about grabbing an alternating series test right away, because the alternating series test would test the overall series. I want to check the absolute value first, because if the absolute value converges, I'm done. Now if you prefer to do these in a different order, that you can. Now the way I'm going to show this is I want to check the series that's my absolute value first. So what I'm checking here then is 1 over k to the 1/2. Okay, well I need to name my series. This is a p-series. This is a p-series with p equal to a half. A half is definitely less than 1, therefore this diverges. So what we have here then is the absolute value diverged. Well, I have two things that can happen now. I have that it can converge conditionally or diverge overall. It cannot converge absolutely. So the second thing I'll do is I'll go ahead and check the series itself. So I'm going to check the alternating series, square root of k. So I name my test alternating series test. I show the criteria for the test. It's non-increasing, and which would mean the next term is less than or equal to the current term. And I'm going to do this with a derivative. There's other ways to do it as well. You could compare term by term. So if I do this with a derivative, this would be k to the negative 1/2 when I flip it up top. So I'd bring the negative 1/2 out front, decrease the exponent by 1. And this k, I'm always plugging in positive values here. So I basically have a negative 1/2 times a positive. This is definitely negative, which is less than 0. Therefore, this is the derivative is negative, which implies the terms are decreasing or non-increasing. They're never equal in this particular case. So check that criteria has been met. Second thing, I need to show that the limit as k approaches infinity of 1 over the square root of k is equal to 0. And that's my other check. Both of these have been met. So therefore, the series, we have to be careful which one we're checking here, negative 1 to the k plus 1 times 1 over root k converges. Okay, so let's summarize what we have here. We have the absolute value diverged, and we have the series itself converged. Therefore, the series converges conditionally. Now if you wanted to, you could have checked this series right away without checking the absolute value, but I've found after working lots and lots of these, if I can check the absolute value first and I find out it converges, it saves me one less test in the long run. It's not always true, but sometimes that in the long run you end up saving yourself some time. Okay, let's look at another problem. Let's look at whether this diverges, converges absolutely, or converges conditionally. Let's look at the series k equal 1 to infinity, negative 1 to the k plus 1, all over the square root of k cubed. Now when we look at the square root of k cubed, we have to remember that's really k to the 3 halves. So the first thing I would do is I would go ahead and check to see what the absolute value does. So I'd look at the sum of the absolute value. So the sum of the absolute value of a sub k. So the sum of the absolute value of a sub k would basically mean I'm checking the series 1. This doesn't look like it's in the exponent, but it is. So this would be k plus 1. So this would look like 1 over k to the 3 halves. Okay, so this is a p series. P series with p equal to 3 halves, which is greater than or equal to 1, which is the criteria for the p series to say that this is divergent. So therefore this diverges. Okay, well that's interesting. Actually, I think I have that wrong. P equals to 3 halves, and this is greater than 1, not greater than or equal to, greater than 1, it converges. I was thinking of a divergent harmonic p series, but this is a convergent. So let's go ahead and double check that. So we have convergent for our absolute value. Then what we can say is that if the absolute value converges, then the series converges as well. So we have two things that we can say here. The series, and it's important to say which series because we're testing two different series. We're testing an absolute value and then the original series itself. So the series converges absolutely. And I'm done. I don't need to check anything else. And this is because if the absolute value converges, the series itself converges. Okay, so this converges absolutely and I'm done. So that's one of the reasons I always check for the absolute value first, because if it converges then you can say absolute convergence and be done. Let's go ahead and look at another example. This one's starting with k equal 1 to infinity. I'm using a trig function here, sine k over k squared. So I think the first thing that we'd probably want to do here, again, we want to check to see does this diverge, does this converge conditionally, or converge absolutely. So what we can do here then is to go ahead and check the absolute value. So this implies that what we're trying to check is the absolute value of the sine of k over k squared. Now k squared is already always positive, so we could even look at it as the absolute value of the sine of k over k squared. So this is what I'm checking. So I need to figure out how to check this series. So I need to go back and I need to think about ratio, root test, limit comparison, direct comparison, p series. I have all those different things. So I'm going to do this by direct comparison. So this is a whole nother test within this test. So I'm going to compare this to, now if we think about the absolute value of the sine of k, sine of k always goes between -1 and +1. It oscillates between -1 to +1. But if I think about the absolute value, it's really only going between 0 and 1. So I should be able to compare this to 1 over k squared. Now if I do that, the absolute value of the sine of k over k squared should always be less than or equal to 1 over k squared, because this oscillates from 0 to 1. So what we have here then is the larger and the smaller. If you remember with our comparison or direct comparison, we need to know the larger or the smaller. So I need to figure out what's going on with the smaller. So now we have to go ahead and check the smaller. 1 over k squared. This is that p series again. P series comes in handy. This is a p series with p equal 2, which is greater than 1, therefore this converges. Okay, let's see if we can draw a conclusion from that. And I can't draw a conclusion because I made a mistake up here. So let's look at this. This is our smaller. This is the less than. So this is my smaller, and this is my larger. So I'll try this again. So I'm checking my larger here. So we have the larger converges. So the larger converges. And then so by direct comparison, therefore the smaller converges as well. Okay, so let's figure out what that means. That means that the absolute value converges. So this implies that the absolute value, the sine of k, over k squared converges. Okay, so right away we know that we're done. So if the absolute value converges, so does the series itself converge. This also implies then that the series, and let's go ahead and rewrite what we have here. Oh, this was in the -1. This is just a mixed sign. Sine k over k squared converges absolutely. Okay, so again, if you check the absolute value right away, if it converges, you're done, and that kind of makes these a lot shorter. Let's go ahead and look at one last problem. I want to make sure that you have plenty to look at before you get started on your homework. Again, we want to determine, does this converge absolutely, does this converge conditionally, or does it diverge? Now we have to be really careful when we're doing these types of problems that you always name your test, and if you noticed on the last couple problems we had a test within a test, so you really have to keep track of things there. Show the criteria for the test, draw your conclusion, whether the test was successful or whether it failed. So here's our alternating series, -1 to the k times k over k plus 1. So to get started here, we could go ahead and check the absolute value, or we could just go ahead and check the series real quick itself. So let's go ahead and check the absolute value. So if we do that, really what we're checking then is k over k plus 1. So if we check k over k plus 1, what ends up happening here then, I think we can use the divergence test on this. Because if we take the limit as k approaches infinity of k over k plus 1, we get 1 here, which does not equal 0. Therefore, the absolute value diverges. And again, we have to have a reason for this, so make sure you include degree in the numerator equals the degree in the denominator. So we have the absolute value diverging. Now, the next thing that could happen is we have to check the series itself. So this could either converge or diverge. So we need to check this, and it looks like to me we could check this using the alternating series test. Now we already know what's going to happen here. If we check this using the alternating series test, we have that the second part's going to fail because this part up here we already took that divergence part, and we see that it's not going towards 0. So I already have an idea that it's probably going to diverge, but let's go ahead and run through the process. So let's look at alternating series test. 1, we need to show that it's non-increasing. There's several ways that we can do this. We can go ahead and remember non-increasing means the next term is less than or equal to the current term. So we go ahead and take the derivative. So this would be the bottom times the derivative of the top minus the top, that's a 1 there. times the derivative of the bottom all over the bottom squared. So if we simplify this, we get 1 over k plus 1 quantity squared. Well, wait, we have bigger problems than I thought we did here. If you notice, this is always positive. So for now, this is always going to be positive, and we need it to be non-increasing. So we have a little bit of a conflict here. So we're going to have to figure out if there's another way that we can test this. So let's go ahead and finish up our reasoning here. This is greater than 0 for k greater than 1, greater than or equal to 1, because if you remember, our indice up here was greater than or equal to 1. Therefore, the alternating series test fails. So I didn't even get to the second criteria. So we're going to have to go after the divergence test. So real quick, we already know the outcome of this. We take the limit as k approaches infinity of k over k plus 1 equals 1, which does not equal to 0. And again, the degree in the numerator equals the degree in the denominator is my reasoning there. So what I could say here then is therefore the series a sub k diverges by the divergence test. So another way we could look at this then is the series terms tend to 0. So the series diverges here in this particular section. So to summarize, we have the absolute value. What did we decide the absolute value did? The absolute value diverged. And we just found out that the series itself diverges. Therefore, I can't say conditional or absolute convergence, it's just diverges. Therefore, the series -1 to the k times k over k plus 1 diverges. Okay, so there's a lot of intricacies going on here. You need to make sure you always name the test, show the criteria for the test, show whether you've met the criteria or not, and then draw some sort of a conclusion. Now, if you can't conclude whether it converges or diverges, you have to go on and try another test. Now, there's a whole list of tests we've learned, and I strongly recommend that you summarize those on your note card before the exam, because it's easy to get them mixed up. And it's nice to have a list to go after, because when you're trying to think about which test to use, if you have a list, you can kind of just go down to the list to check for some of those. As usual, good luck while you're working on these. If you have questions, please let me know. I'm happy to help. You can also use your Pearson Connect to a tutor from my math lab, or I'm also happy to set up a meeting online if you would have any questions, or can text me questions as well. Good luck and enjoy working with these series.